Okay, we're going to talk about anti-Markovnikov addition to alkenes, specifically of hydrogen halides. So what does anti-Markovnikov addition allow us to do? It allows us to get the functional group on the less substituted position. And it usually involves some special reagents so that we can do that. So in the case of hydrogen halide, which I'm going to do first, and then I'll do anti-Markovnikov addition of alcohols or water to form an alcohol to alkenes after this. So the first thing that we do is this is the overall reaction. And what we do is we use HBr with peroxides and heat. And the first part is the initiation, where we actually do some free radical chemistry. And this sets up the reagents to perform the anti-Markovnikov addition. So the first step is we have homolytic bond cleavage of the peroxide. And then the peroxide will react with the HBr to form the bromine radical. The bromine radical then is what reacts with the alkene to give us the anti-Markovnikov addition. It reacts with the alkene to give us a secondary radical, or the more stable radical if it were a different, different alkene. It's just like the same justification for Markovnikov addition when we form the more stable carbocation intermediate holds here, where we want to form the more substituted radical. It's the most stable. And then once we have that radical, it then reacts with more HBr by pulling off the hydrogen, and we get more bromine radical produced. And that will just continue a cycle until we get termination, which you can figure that out from what we've done before with free radical halogenation of alkenes. Okay, I'm going to erase this board and go ahead and make the hydroboration oxidation mechanism so you can see that one. Okay, we're going to do the Markovnikov mechanism now. One note I wanted to make from the previous part when we did the peroxide with HBr. Note that HCl does not react with peroxide in the same way. So when we do the anti-Markovnikov with peroxides, we don't use HCl. So moving on with the anti-Markovnikov addition of water to alkenes, remember that we have syn addition of the H and the OH of the water that we're going to add. And you can see that in this step right here, that this H and this B are adding to the same face of the molecule. And down here I could show that as in the final product. I could actually draw the hydrogen in there, but you should just be able to assume and know that that's there. So starting out with the mechanism, we have the first part, which is the oxidation, or not the oxidation, but the boration, the hydroboration. So what that means is we're adding a hydrogen and a boron. So the most electrophilic atom in the HB3 is the boron itself. It's actually less electronegative than the hydrogens. So because it's electrophilic, the double bond attacks that atom. And one of the bonds between the boron and the hydrogen will actually be nucleophilic and attack this tertiary position. Because when this attacks there, we get a large buildup of partial positive charge here. It's almost like a carbocation. And you can kind of expect that if you were to just add HBr to this molecule by itself, we would put a hydrogen here and get a carbocation there. Well, the same kind of thing happens. We get a larger partial positive charge, getting us carbocation-like character, and then we get electrons that go in and attack that position. This bracket means intermediate, so this is the bonds being broken and the bonds being formed in the molecule until we have this part right here. And once again, this hydrogen and boron, that's where the boron gets replaced there. They're on the same side. I just didn't draw the hydrogen. So this red part is the hydroboration part. The blue part is the oxidation. And we have an initiation step for number 2 here, where the hydrogen peroxide, and note that this is hydrogen peroxide specifically. It's not just some random peroxide. It has to be hydrogen peroxide. It reacts with the hydroxide to form this negatively charged peroxide type species. It comes in right here, and it will actually attack the boron, which is, like we've already established, it's electronegative. And so we get this intermediate as a result. And for reasons that I don't quite understand, we get this bond walk of a mechanism where this bond between this carbon and this boron will actually form between that oxygen. And when it does, the OH group will fall off. But the boron is still bound to this oxygen. And so we see that this bond is now this bond is, instead of being bound to the boron, is now bound to oxygen, we see, but the oxygen is still connected to the boron right there. So this sets us up to do basically to have our final product, but we just have to do a couple things to get this boron off. So a hydroxide, which is in solution because of this, it comes in and attacks the boron and causes it basically to leave the oxygen. We have a negative charge now, which, by the way, we're forming a lot of negative charges, you'll notice, which we haven't really done before. But it's okay because we're in such a basic solution because of this. So if that seems strange, maybe it should, but it's okay in this situation because of what our solvent is. Okay, so now that we have this guy, we're going to basically do initiation again, but we're going to do it with this oxygen. It's going to deprotonate one of these to give us our final product and more of this right here. And that's hydroboration oxidation.